Hello and welcome back. Excuse me. Today we're going to do section 9.5 in your Varberg text. It's called Alternating Series. And the reason we're studying these series is because it becomes very powerful pretty soon. The next section actually is called Power Series. And when we alternate them, they really are interesting. So an alternating series is a series such that where you start out and then you subtract. AC3 minus AC4 plus AC5. The signs are alternating, etc. And where each individual is greater than 0. Each A is greater than 0. So we're going to take one and subtract it and add it and subtract it and subtract it. So it's an alternating series. For example, the alternating harmonic series. Well, the harmonic series is we start out with 1, and then we're going to subtract a half, add a third, subtract a fourth, add a fifth, subtract a sixth, etc., etc. It's called the alternating harmonic series, and we'll talk about that again in just a little bit. So let's go to the alternating. There's something called the alternating series convergence test. Alternating series convergence test. And it's just two parts to it. Suppose you have a, where are we? Suppose you have an alternating series. And incidentally, I guess I haven't discuss this right now. We're going to write it like this: -1 to the n of a sub n. This makes it alternating. The a sub n's are all positive. The first one, well, actually, you'd start here with 0, I guess. The first one, it doesn't matter. They alternate. So that suppose you have an alternating series such as that, and two conditions apply, where each a sub n is greater. This thing's getting, this is decreasing. The a sub n's are decreasing. Where that's true, and 2, the limit of any of the individual a sub n's as n goes to infinity is 0. Whoops. Then that series converges. A sub n. You know, we'll put the -1 in. Converges. Definitely. The reverse, by the way, is not true. We'll talk about that. Furthermore, here's a nice little thing. Furthermore, the sum of any n, the error in the sum, in the partial sum. The error in the partial sum, S sub n, is less than the next term. If I was to add these 5 up right here, 1 plus 2, add those up, the error in the actual sequence is less than 1/6. That's what that's saying. It's powerful. You can then, you could start with the error then and determine how many in the series do you need to get less than that error. Okay, so we're there. Alternating again. Alternating harmonic versus sum of the first n term. Okay, so, the alternating harmonic. Note. Alternating harmonic. Looks like that. The series is 1 minus a half plus a third minus a fourth. Now, from the alternating series convergence test, there's 2 things that are true. 1, clearly, these are they're getting smaller. A half is bigger than a third, bigger than a fourth, bigger than a fifth, etc., etc. Clearly, it's getting smaller. 2, the limit, as n goes to infinity, 1 over n is 0. So this converges. Alternating harmonic converges according to the alternating series convergence test. It converges. However, the harmonic sequence diverges. And this is going to be called conditional convergence. With the last part of this particular table, we're going to talk about conditional convergence, where the alternate series converges and the regular positive series diverges. But before that, let's go to absolute convergence test. As opposed to conditional, we're going to classify series into three. Absolute convergence, conditional convergence, or divergent. And so this is the absolute convergence test. Absolute, all it's saying is you have A sub n is alternating if the series, A sub n, the absolute value of that, which is the positive part of this, it's not alternating anymore, it's all plus, converges, then so does the alternating. So does the alternating series. Absolute convergence. If this one converges, of course, it's going to converge. Alternating or conditional versus absolute. And so this is a conditional one. It just show this. For example, show 1 over n squared. Sorry for that. Alternating converges. And it does. There's no doubt about that. All we have to do is look at, and that converges without being alternating. That converges because of the p-test. Then so does the alternating series also converge. So right here, all the because of the absolute convergence test, everything we talked about is on the table. All convergence tests apply right now. Because if you can get a positive series to converge, then certainly the alternating series converges. And in particular, how about the ratio test? Let A sub n be alternating. Well, we're going to use the ratio test. Then you take suppose A sub n plus 1. The absolute value of A sub n plus goes to a limit L. Suppose the limit of this goes to some number L. Then the ratio test says if L less than 1, convergence. If L greater than 1, divergence. Equal 1, no, inconclusive. And so what we're going to be doing is testing for conditional convergence. Test series, what we want to do is test, and I'll do examples of this in the next video. Test series for convergence. And when we say convergence, 1, absolute, 2, conditional, or divergent. And actually there are some you can't tell as well. And an absolute is if. If the positive one converges, then they both do. Conditional is if the positive one diverges and the alternating one converges. Then it's called conditionally convergent. And of course, divergent is the third category. I think we're going to stop there. Oh yeah, let's stop there.